So we're going to continue talking about strain, and I'm going to make a sort of a general point. Let's say we find a rock or some that's clearly undergone some strain. Let's say it's got a lot of, we could represent like a an object that was in it that's now become ellipsoidal. And the point I want to make is that there's lots of different ways that this any kind of homogeneous strain will make an ellipse out of an original circle, or in 3 dimensions, an ellipsoid out of an original sphere. So one way we could get to this state would be if we took something and we just, in one step we squished it down, right? That's one way to do it. We could also potentially take something, shrink it down, and then stretch it out. And so the strain history, there's a difference between the final strain that we see and the strain history, which could take different paths. And I also point out that shearing, we always draw these nice, the box around it. You can see that the shear strain has happened. But oftentimes we don't. Nature doesn't come with these boxes. So if you just zoomed in, this ellipse looks exactly like that one. Okay, so the point here is many strain paths can lead to the same final strain. Okay, this is just a general principle to keep in mind as we go forward. Let's talk about 3D strain. Okay, so we saw earlier, we defined S1, S2, and S3 as the stretch values, from largest to smallest. And we can classify strained rocks in sort of 3 general types. And there's sort of the official name, prolate is one of them. Don't need to remember that necessarily. Cigar shape, I think, works just as well. And in this case, the largest of the stretches is it's bigger than the sort of intermediate one, but the intermediate one and the smallest one are about the same. So this is also called constrictional. Okay, so for constrictional, we start out with a cube. We end up with a pencil. Quite. Let's try that again. I still didn't manage to do it. There we go. A little bit of a pencil, okay? So that's one sort of 3-dimensional strain. So why am I saying make that even longer, okay? So it's clearly so we're conserving the volume here, although constriction doesn't always have to. But I just want to emphasize that in 3 dimensions, no side of this is staying the same. So it's 3D strain because S2 is not equal to 1. So here we have on this side S2 and S3. So we refer to these both as the sort of the magnitude, the number that you could calculate. Okay, this line is gotten shorter on this side. And we also refer to it sort of as the axis, like in 3 dimensions. We can refer to the directions S1, S2, and S3 here. And then the long one, so it's S1 because it's the biggest. It's the one that has gotten longer. So none of these is equal to 1. So this is not plane strain, it's 3D strain. Okay, that's one type. And here's another type. Oblate. So in this is the pancake shape. So here we have S1 is roughly equal to S2, and those are both quite a bit bigger than S3. Okay, so here our cube turns into a thing like this. Okay, so this is also definitely a 3-dimensional strain. See if you can label, like I did up here, the axes of the sides of this. Maybe pause the video for a second. Okay, so the two that are about the same, S1 and S2, and then here we have S3. And just pause for a second and make sure you know how to calculate all these values. How would you calculate S1, for example? You might want to pause and think about that for a second. I'm going to just clarify that this, there we go. Okay, right, so S1, how would we measure that? We'd measure this distance. Let's say that distance is 6. Okay, and then we would compare it to how it originally, the original length, which is maybe 3, and we would say, oh, okay, the numerical value of S1 is length final over length initial. It's 6 over 3 is 2. So the stretch value, the magnitude of S1 is 2. And whereas and S2 is similar to that. S3 would be a number less than 1. All right, and then the third type of 3-dimensional strain is probably the most common. It's called general or blade shape. And here we have S1 greater than S2 greater than S3. And you can kind of imagine what this would look like with our original cube. So it's definitely gotten longer in one dimension, but none of the sides are equal. So when in a special case of this, when S2 equals 1, we have what we talked about before, plane strain. Okay, so if S2 doesn't change, it's plane strain or 2D strain. And I should also note sometimes these are referred to as the S1 is referred to as X, S2 as Y, S3 is Z. And there's a nice diagram. 3D strain. We use it's called the Flynn diagram. And axes are a little bit strange. If you take the value of S1 divided by S2 on the y-axis and then on the x-axis, you can work out why this makes some sense. But it turns out that, so there's a one-to-one line. Up here, we get constriction, and down here we get pancakes. And we could take any homogeneous strained object and plot it on here. So this is a good way to compare the strain you see in some rocks to those in other rocks. And along this line, this is the plane strain, 2D strain. Okay, so in other words, where S1 equals 1. And so the further you are along this axis, the more extreme. The further you are from the origin, the more extreme it is. Like, so the larger sort of the pancake, the thinner it is, or the longer the linear aspect. And one other convention you should know about, so this has a sort of, has kind of a linear feature, right? So we call rocks that look like this L tectonites. So tectonites, rocks that have been deformed. L tectonites have a strong linear feature, and S tectonites have what we call foliation. So foliation, like folia, like are leaves. So like, think about sheets of paper, layers. So here, the layer, like the planar feature, is dominant over the linear. And here the linear is dominant over the planar. And then if we're in plane strain, they're fairly equal. We call them LS tectonites, and they're quite common. Often we are looking at rocks that fall fairly close to plane strain. So in LS tectonites, lineation is generally parallel to S1. Oops. And foliation, the layering, is the S2, S3 plane. Okay, so this is just to sort of point out a subtlety that if we find linear features in a rock or planar features in a rock, they don't necessarily exactly correspond to the sort of theoretical orientation. Their orientations might be off a little bit, but that's a detail that we don't get into in this class. For the most part, you can just assume that in constrictional strain that if you find a bunch of features that have a linear aspect, that is S1, and that the plane here is the S2, S3 plane. Let's look at a few slides. So here we see some conglomerates. So conglomerates are these coarse chunks of different rock materials, sedimentary rock, and this is one that's not been strained or strained very little. So you're looking at some sedimentary layers. And then here's a rock that's been a conglomerate that's been strained a little bit more. So you can still make out the class pretty clearly, but they're starting to have a similar long axis direction and short axis direction. And what often happens is some of these clasts are stronger than others. So here's one it's relatively strong compared to everything around it. So you can see how other clasts have been sort of smushed around it. The camera lens for scale. But overall, the strain is increasing. So if you measure the stretch here, it's going to be a larger number than here. And then here we have sort of the highest strain shown in the rock. So many of these, here's one going from here, classed, potentially all the way to there. Some of these, here's another this white one's pretty elongate. So these are pretty typical from, this is what happens to rocks beneath faults. If you went down below the San Andreas Fault 10, 20 kilometers, the rocks are experiencing strains like this. And so it's useful to be able to quantify the amount of stretch and the type to understand how deformed the rocks have become. Here's, using the XYZ convention, some examples of 1D, 2D, and 3D strain. So we've talked about 2D strain. Okay, so we're starting with this yellow box, not quite a cube, but that's okay. And we're squeezing it. That material we're conserving mass. It squeezes out two sides, but in this dimension, it doesn't change. Okay, so that's plane strain again. And then here we have constriction. Here we have or cigar shape strain. Here we have flattening, pancake type. And then you could also go into 1D as well. And in this case, you need to lose material or gain material. So, which is less common geologically, or at least harder to sort of measure or estimate. Here's a Flynn diagram showing similar boxes to what we see before. Here we start with cubes. We have plane strain, we're going into constriction, going into flattening. And these show examples of different tectonites. So S-tectonite, if you take out these, this is made of a bunch of basic little pancakes piled on top of each other. Whereas this is the L-tectonite, and constriction is like a bunch of pencils held together. And then the LS is a combination. It's basically pancakes, but they're a little bit longer in one direction of the flat part than the other.